Imagine a robot arm assembling a car or a robotic surgeon performing delicate surgery. These are examples of manipulator mechanisms in action. Manipulator mechanisms are essentially robotic arms designed to interact with and manipulate their environment. They are composed of links connected by joints, mimicking the structure of a human arm. These mechanisms grant robots the ability to grasp, move, and manipulate objects with precision and control. From industrial automation to healthcare, manipulator mechanisms are revolutionizing various fields. These mechanisms are becoming increasingly sophisticated, driven by advancements in areas like mechanical design and control algorithms. A key focus of this progress is the enhancement of degeneracy and dexterity, two crucial properties that significantly impact a manipulator's capabilities and efficiency. Understanding these concepts is key to unlocking the full potential of robotic manipulators. In robotics, degeneracy might sound like a negative term, but it's not always a bad thing. Degeneracy refers to a state where a manipulator mechanism loses one or more degrees of freedom. A degree of freedom represents the ability of a joint to move in a particular direction. For example, a human shoulder has 3 degrees of freedom. It can move up and down, forward and back, and rotate. When a manipulator is in a degenerate configuration, certain movements become restricted. Imagine a robotic arm fully extended. It loses the ability to move its end effector, the hand of the robot, in certain directions. While this might seem limiting, degeneracy can actually be advantageous in specific situations. Degeneracy, while seemingly restrictive, can be strategically employed to enhance robotic manipulation. One significant advantage lies in increased stiffness and load-carrying capacity. When a manipulator enters a degenerate configuration, specific joints lock, essentially creating a rigid structure capable of withstanding higher forces. This property proves particularly valuable in tasks like heavy object manipulation or precise positioning where minimal movement is desired. Moreover, degeneracy can be leveraged to simplify control algorithms. With fewer degrees of freedom to manage, the complexity of calculations required for precise movement is reduced. This simplification translates to faster processing and potentially smoother motions, enhancing the overall efficiency of the robotic system. The practical implications of degeneracy become evident in various real-world applications. Consider a robotic arm tasked with welding a car chassis. By strategically positioning the arm in a degenerate configuration, the welding torch gains increased stability, resulting in a more precise and robust weld. The inherent stiffness provided by degeneracy ensures minimal vibrations or deviations, crucial for maintaining weld quality. Another example can be found in robotic surgery. During a delicate procedure, a surgical robot might assume a degenerate configuration to fix its position relative to the patient. This stability is paramount for minimizing tremors and ensuring the surgeon's movements are translated with utmost precision, reducing the risk of complications. Section 5. Defining dexterity in robotics. Dexterity in the context of robotics refers to a manipulator's ability to execute complex movements with agility and precision. A highly dexterous robot can navigate confined spaces, manipulate objects with intricate geometries, and adapt to dynamic environments. This characteristic is crucial for robots operating in unstructured settings, where adaptability and versatility are paramount. Dexterity encompasses various aspects, including the number of degrees of freedom, the range of motion of each joint, and the ability to coordinate movements effectively. The more dexterous a robot, the wider its range of potential applications, and the more complex the tasks it can perform. Section 6. The significance of dexterity. The importance of dexterity in robotics cannot be overstated, particularly as robots transition from structured industrial settings to more dynamic and less predictable environments. In fields like healthcare, manufacturing, and exploration, robots are increasingly required to interact with complex objects and navigate challenging terrains. For instance, consider a robot designed for disaster response. High dexterity would enable it to navigate rubble, manipulate tools to clear debris, and even perform delicate tasks like opening doors or shutting off valves, actions that require a high degree of flexibility and precision. Section 7. Dexterous robots in action. Dexterous robots are already making significant contributions across various sectors. In advanced manufacturing, Robots equipped with multi-fingered hands and advanced sensors can assemble intricate electronic components with human-like dexterity. These robots can handle delicate parts, apply precise forces, and adapt to variations in component placement, leading to increased production efficiency and product quality. In healthcare, dexterous robots are assisting surgeons in minimally invasive procedures. These robots can access confined spaces within the body, manipulate surgical instruments with precision, and provide surgeons with enhanced dexterity and control, leading to faster patient recovery times and reduced risk of complications. Section 8. The interplay of degeneracy and dexterity. While often considered separate concepts, degeneracy and dexterity are interconnected, and their interplay significantly impacts a manipulator's overall performance. Understanding how these properties complement and influence each other is crucial for designing and controlling highly capable robotic systems. For example, a robot might strategically utilize degeneracy to enhance its dexterity in specific tasks. By temporarily locking certain joints, the robot can gain increased stability and precision, allowing it to perform delicate manipulations that would otherwise be challenging with a fully articulated arm. This dynamic interplay between degeneracy and dexterity enables robots to adapt to a wider range of tasks and environmental constraints. Section 9. Conclusion: Shaping the future with advanced manipulators. The advancements in manipulator mechanisms, particularly in the areas of degeneracy and dexterity, are revolutionizing the field of robotics. These sophisticated systems are no longer confined to structured industrial settings. They are now venturing into our homes, hospitals, and even outer space, expanding the horizons of what robots can achieve. As research and development continue, we can expect even more innovative manipulator designs with enhanced capabilities. Imagine robots capable of performing intricate surgeries with minimal human intervention, robots that can assist in disaster relief efforts with unparalleled dexterity, or robots that can explore the depths of our oceans with unmatched precision and adaptability. The future of robotics is brimming with possibilities, and the continued exploration of degeneracy and dexterity will undoubtedly play a pivotal role in shaping this exciting frontier.